In this recording, we'll discuss a few examples for Newton's third law of motion. Okay, we'll start with the weight. Look here in this graphic what I did. I drew the Earth as a large sphere, and I drew an object on top of the Earth. They are not to scale, of course, obviously, but at least it gives us an idea. What we defined as the weight before is a force that the Earth exerts, that the Earth as a whole exerts on the body. And that force is going to point towards the center of the Earth. It is represented by yellow here. Now, look at the labels here. It's a force exerted by the Earth on the ball, FEB. That one we said we call it's FG, it is mg in our case, at the surface of the Earth, where g approximately equal to 10 meters per second squared. And we also figured out how to calculate it with another expression, g m1 m2 over d squared. We have showed that we can use that expression as well to calculate that force. Now, what's the reaction to that force? Okay, we have the ball sitting at the surface of the Earth, and then there is a gravitational pull on it. What you need to remember from Newton's third law of motion, only the two objects that are interacting are going to be responsible for both the action and reaction. Now, the action here was exerted by the Earth on the ball, so the reaction should be by the ball on the Earth. So it should be a force exerted by the ball on the Earth that's equal to the force that the Earth exerts on the ball and opposite in direction. We have them here, one in yellow and one in red. These two are equal to each other, but opposite in direction. Now, just to make sure we understand this, so if the ball is going to have a weight of 100 newtons, that would be the action. The force that the Earth exerts on the ball is 100 newtons. The reaction, the ball is exerted on the Earth 100 newtons. It's exactly the same force, opposite in direction. Now, of course, the 100 newtons are going to affect the ball much more than the Earth, because the ball has a much smaller mass than the Earth is. But both of them are going to be subject to that 100 Newton force. Okay, let's move on. Now, what about the normal? When I have a ball sitting on the Earth like this, at the surface of the Earth, there is a normal force exerted on it. But what's going to exert that normal force? It is not the Earth. And this is why I was making the distinction before, and that's a very important distinction. It's going to be the floor. If it is on a desk, it's going to be the desk. If it is on a ramp, it's going to be the ramp. What exerts the normal force is the surface. In this case, it's going to be the floor. So the floor is going to exert a normal force on the ball. The reaction would be the ball exerting a normal force on the floor. So both of these are normal forces. Both are of the same nature. They have nothing to do with the gravitational force. The reaction to a normal force action is a normal force reaction. And that's what we have here. That's what's represented by this graph. Now, what if I have an object in free fall at the surface of the Earth? What would be its weight? Same thing as we had before. A force exerted by the Earth on the ball. And the reaction is a force that the ball exerts on the Earth. It does not matter if they were touching or not. The gravitational force is not a contact force. So it's the same force, equal in magnitude, and opposite in direction. And it's going to be, the magnitude is going to be the weight of the ball at that point. Now, what about the normal force here? Not touching anything. If it is not touching anything, that means no normal force. Okay, so we don't have to worry about a reaction if there is no action to begin with. Okay, now to illustrate this a little bit more, we are going to take this example of these three blocks that I had before, but in this case we are going to investigate the boxes one at a time. Okay, now we have the whole setup at rest. Okay, so they are not moving, they are at rest. And the question, what are the forces on the blue box? The forces on the blue box, there is going to be the weight, which is the force exerted by the Earth on the blue box, and we said we call it Fg usually, and the green box is going to exert a normal force on the blue box. That normal force, we know it has to balance this force. How do we know that it has to balance it? Because this box is not accelerating. If it is not accelerating, the forces acting on it should be balanced. So in this case, what that means, we have a force of the green on the blue box. That's going to be equal in size to this one. Now it is pointing upwards because what the green box is doing is holding the blue box up in position there, and it is a normal force. That's why I'm going to write it as F sub n. Okay? These are the forces acting on the blue box. Now they are balanced. They are not action-reaction pairs. Both of them are two separate forces acting on it that are balanced. Now, what are the forces on the green box? Okay. This is where it's going to start becoming a little more interesting. Okay, what are the objects that exert forces on the green box? Like for the previous case, it's going to have a weight, a gravitational pull due to the Earth. So what that means, I'm going to have a force exerted by the Earth on the green box. Okay, now, what else? We said in the previous screen that the green box is exerting a normal force on the blue box. There must be a reaction to that. Notice here I'm not drawing them in the same screen so we don't confuse things. If I'm worrying about the green box, I have to deal with it separately than the blue box. I should not put them all together in one shot. But from here, if you remember, we said the green box exerts a normal force on the blue box. So as a reaction, the blue box should exert an equal force on the green box. So what that means, the blue box is going to be exerting a normal force in the downward direction on the green box. Now, that's not the end of it. The green box is touching the red box. Now, if it is touching the red box, that means the red box should be exerting a normal force on the green box. Now, that normal force, the red box is supporting the green box, meaning that that normal force should be pointing upwards. F red on green. Now again, since we don't see the green box moving up or down, that tells us that these forces are balanced. We have two forces pointing down and one force pointing up. So the force pointing up, FRG, should be equal to the forces pointing down, VBG, plus FEG. Now, just as a reminder to make sure, this is a normal force. This also is a normal force. And this is a gravitational force. Okay? That's the green box. Now, what about the red box? So now that we have investigated the green box, the red box is going to be treated somewhat similarly. Now, we have the gravitational force acting on the red box. So that's F Earth on red. And then we have the green box is going to react to this FRG that we talked about in the previous screen. So instead of that FRG, I'm going to have a reaction to that. That's going to be F, the normal force that the green box is going to exert on the red, so FGR. And then there is the floor. The floor is going to exert a normal force supporting the red box, and that normal force is going to point upwards. F floor on red. Now again, since the red box is not accelerating up or down, these forces need to be balanced, which means the force pointing up, which is in this case FFR, floor on red, is going to be equal FGR, green on red, plus FER, earth on red. This is a normal force, remember? And this is a normal force as well. And this is a gravitational force. Okay, let's investigate this further. In these cases, we didn't have any horizontal motion, so we dealt only with the vertical. Now, we still have no motion, but we are pushing on the red box. How is that going to change? I'm not going to use several screens as I used before. I'll try to use the space here wisely. So for example, here we are going to talk about what's acting on the blue. Here we are going to talk about what's acting on the green. And on the graph, we'll talk about what's acting on the red. Okay, let's talk about the red first, since it's fresh on our heads. Okay, we have balanced forces. No motion. It means all forces are balanced along the vertical and along the horizontal. We discussed the vertical forces, so I'm going to quickly just draw them. F Earth on red, and then we have F green on red, and then I have F floor on red. Now we have this push here exerted by this thin fellow, so we call it FP on red, push on red. Now, since we don't have any motion, this push must be balanced. It's going to be balanced by what? By a static friction force. So, who's going to exert that static friction force? It's going to be the floor. Okay, so our symbols are not enough, but so we are going to have a friction force That's going to be exerted by the floor on the red. Okay. Now, let's discuss the blue one. Okay, I'm not going to redraw the vertical forces. We can go back a few screens and see them. But along the horizontal, do we have any force acting on it? And the key point here, there is a resounding no. Nothing is pushing it, nothing is pulling it. We don't see any evidence of any force. We don't see it accelerating. If it were accelerating, that should tell us there must be a force. But there is no acceleration, no motion. No motion, it means everything should be balanced, and I don't see anything acting on it. So there is no forces along the horizontal. The same is applicable for the green. We don't see any acceleration. That means there is no horizontal forces acting on it. You know, the fact that we don't see any acceleration and we don't see any force. If we see any force, we have to find what's balancing it, like we found what's balancing the push here for the red one. Okay? Now, what about if they are moving at constant velocity? If they are moving at constant velocity, everything is the same as the previous screen, except for one thing. This force, friction that the floor exerts on the red, in this case, it's going to be kinetic friction instead of static, like in the previous case. But everything else is balanced, even though these are moving. Remember Newton's first law. Even though that these are moving, there is no force acting on them on the horizontal. We don't see one. If there is no one, there is nothing to balance it. So we have only forces along the vertical, on the blue one, and on the green one. Okay, that's a little tricky. What about if they are accelerating? Now the case is a little more complicated. If they are accelerating, then when we look at the blue one, okay, for the red one first, let me, before discussing the blue one, and we might need to revisit the red one, we have the vertical forces that we agreed on before, we have the push that we agreed on before, F push on red, we have kinetic friction, floor on red. Now the difference, we don't have a balance along the horizontal for the red. We are not sure yet if we might have other forces acting on it from the top along the horizontal. We have to check that out. But for now, we know that these forces exist, these two forces, but we don't know if they are balanced or not. Let's check the blue one. What's happening with the blue one? We see it accelerating. If it is accelerating, that means there must be a net force acting on it along the horizontal. Now, if there is a net force acting on it, who's going to exert that net force? Okay, when you examine things carefully, there is nothing but friction between the green and the blue box that's capable of exerting that force on it. There is nothing touching it. There is nothing affecting it except the green box that can affect it along the horizontal. So, and this is the interesting part. So, that static friction force is the one that's going to be responsible for the acceleration. So it must be in what direction? The same direction as the direction of the acceleration. Okay, and it is static because the blue box is not sliding off the green box. So in other words, there must be a friction force, it is static, that the green box exerts on the blue one. Isn't that interesting? And that force should be equal to the mass of the blue box times its acceleration, which is the same as the acceleration of all of them. Isn't that fun? Now let's look at the green one. It is accelerating as well. So that means the forces are not balanced. Okay? Now, it is accelerating in the same direction as the rest. So it must have an unbalanced force along that same direction. What are the forces that are acting on the green? Along the horizontal. The vertical ones, we dealt with them already. Let's not worry about them. Along the horizontal. There must be a reaction to this force here. Let me change the color of my pen. There must be a reaction to this force. So there is going to be a friction force opposite to this one. It is again a static friction force that the blue one exerts on the green one. Okay? What's interesting is, when you look at this force, it's opposite to the direction of the acceleration. So it cannot be the one responsible for the acceleration. So we have to look elsewhere. Okay, we are going to look elsewhere. So we are going to look at the bottom. I'm going to change the color of my pen so we can see what I'm writing. Okay, let's go blue now. Okay, come on. So we are going to have to look at this interface. So what this tells me is the red one must be exerting a static friction force on the green one, F red on green. Okay? There is no other thing that can exert forces on the green one. So what we have for the green one, along the horizontal, static friction force due to the red, plus static friction force due to the blue, is equal to the mass of the green times 8. And remember, this one is going to be negative. Isn't that beautiful? Okay, now let's focus back on the red. Why do we have to focus back on the red? Because of this one here that we just drew. What did that one tell me? It told me that the red one is exerting a force on the green. So there should be a reaction. If it exerted a force on the green one is exerting a force on the red one. And let's go back to the black color. So what is it going to be? It's going to be equal to this one, but opposite in direction. It's going to be again static, and it's going to be green on red. So we have suddenly an additional force acting on the red one that we didn't have in the previous cases. Now, what's balanced for the red? We have on the positive direction the push, and then we have on the negative direction the static friction due to the green, plus the kinetic friction due to the floor, and those, they should be equal to the mass of the red times A. And remember, this one is going to be negative, and this one is going to be negative as well. The only one that's positive is FPR. Okay? You might have to go over this a couple of times. It's a little tricky, this concept here that I explained, but it's not rocket science. It's just the concepts are a little tricky, and you can handle it. And again, it's conceptual, but it's difficult. Now, just this is a quick question before we kind of finish discussing these three blocks. What would happen if I don't have friction between the blocks? It is slippery there with no friction. Okay, start getting the idea. There is no friction. Okay, this one is going to accelerate by itself. Then these are going to stay in position. An object at rest will stay at rest unless acted upon by an unbalanced force. And since there is no friction, there is nothing to exert on them an unbalanced force, so they are going to stay in place. That's why a lot of times people leave stuff on the back of a truck and then they find their way on the road and stuff like that, because there is not enough friction to accelerate them forward. No friction to accelerate them forward, they stay in place. In this case, if they stay in place, they're going to fall on the road. Okay, one last thing here. We have two gentlemen working hard at trying to get supper, especially with these economic hard times. Probably we all need to be doing that if there is any fish left. But anyway, so we have the bald man and the hairy one. Now, who's exerting a force on the fish? We don't see the fish here, but who's exerting a force on the fish? The line. None of them is exerting a force on the fish. Remember, for any force, you have to account for it by seeing whatever exerted that force. If you don't see something touching it, if it is not a gravitational force that acts at a distance or a magnet that acts at a distance, if you don't see the reason for the force, if you don't see something touching it, then you don't have that force. Now here what we have, the red shirt person is exerting a force on the fishing equipment. The green shirted person is exerting a force on the red shirted person. Of course, they are both exerting forces on the floor as well, but it can be fun to try to examine all of these cases. But we're not going to get into that fun right now.